Hi, I'm Stefan. I'm a quantum education manager at IQM Quantum Computers, and today I'll show you what we as a company do and how you actually build quantum computers. So that's what we do. We build quantum computers. But why? Why the hell should we build quantum computers? And actually, the thing is that there are some problems which are just intractable for classical computers. Like, it's not only that you can't solve them efficiently, but you can basically never solve them in your lifetime. So, and there are just fundamental limits on what we can achieve, because there are just not enough atoms in the universe to build a large enough memory. In addition to that, we run into time and power limits, even though the calculation might finish in a couple of months or years. It's probably too long because we need the result much faster. And those applications, they spread through a lot of different fields, from chemistry to finance applications, to biology applications. And those are a lot of problems that we as humanity would love to solve. So who needs that stuff? Actually, we all do, or more precisely, HPC centers do, as they support us to create new insights in science and technology. So HPC centers, high performance computing centers, they solve the challenges of tomorrow. With help of HPC centers, we simulate climate change or crash simulations, we do drug discovery, or we do solve optimization problems. And this is a great market also. And of course, HPC centers want to provide their customers the latest and greatest. And this also includes now quantum technologies, which 76% of HPC centers want to provide to their customers. And we as a company, we just do that. We build quantum computers for research institutions like here in Finland. We built Finland's first quantum computer, but also for supercomputing centers like we did in a project in Germany. But now the thing is, how do you actually build quantum computers? And building quantum computers, that is not only a complex task, but it really is done on multiple levels. So on the base level, you have the chip itself, you create the qubits you've heard of yesterday. That's where the actual computation happens. But of course, just the chip will bring you nowhere. What you need is control and measurement electronics that help you to control your qubits, make operations, perform operations on them. Then you need an interface where you can make the computations or describe the computations in a programming language. And that's probably something you'll explore in the next couple of hours. And at IQM, we do the whole chain. So we start at the chip design, and we use our own platform to do the chip design. If we have a design we're happy with, we take it to our quantum foundry in Finland. And that's actually pretty important because quantum processes are very complex to manufacture, and for public clean rooms, this can become pretty difficult. And when you get your chip out of this factory, you cool it down in one of those huge cryostats or fridges, where you put the chip down there and you cool it down to 10 millikelvin. So that's really colder than outer space and close to absolute zero. And of course, then you put this into some shelves, some metal shields around it to protect it from environmental noise. So everything that could interfere with our qubits, we try to protect it from them. And then you could add some fancy lighting as we have here in our lab. And then it comes to the interesting part. So next step would be that we write our own program, and we can use whatever language we want to use. And in that example, I just use Qiskit for that. And every program just starts on a regular computer, on a notebook, on a server with a classical hardware behind it. And we do the same that we do with any other computer program. We write code that specify what operations are performed on which qubits. So essentially, in this little example, I create a circuit with 2 qubits. So I just do operations with 2 qubits, and then I perform 2 operations. One just involves 1 qubit with index 0, and the other operations involves an operation operating on 2 qubits, 0 and 1. And this is then transformed into microwave signals. And those microwave signals, they will control the qubits down in the chip. And we'll now follow one of those microwave signals down into the quantum computer. So we start at the control electronic side, and the signals are generated, sent to the chip, and now we see how it goes into the fridge, down through the different layers that step by step cool down the system until we reach the 10 millikelvin we have down at the chip level. And here we see one of those layers, and at some point those signals reach the chip, as we see here, and help us to perform all kinds of calculations that could improve how we do simulation, how we do optimization, how we might do machine learning also. And the question now is, this is of course not the whole secret. Building a quantum computer is probably not as easy, but it really requires a whole team of people, and that's actually the superpower we have at IQM. We have a team about 200 people in size now, with more than 80 PhD level professionals. We educate our own PhDs, and of course it just works because we all trust each other. There is collaboration going on, and we have the ambition to create something like a quantum computer. And what we really embrace is diversity, not only in terms of backgrounds. So people really have diverse backgrounds coming from all types of study programs, professional expertise and stuff, but also from different nationalities. So at the moment, those are the 37 different nationalities we have at IQM. And of course, we are hiring. So if you feel that you in some way want or can contribute to quantum computing or to where IQM is heading, then feel free to check out our careers page and learn what opportunities we have for you in Espoo, Finland, Munich, Germany, Madrid, Spain, or Paris, France. And thank you now for tuning in, and have great fun hacking. Either it is about hacking or using a quantum computer to generate levels, or if it's about having one of those principles that make quantum computing, actual quantum computing like superposition or entanglement, as an element in your game. It doesn't matter. I'm really curious to see what you'll create, and I wish you all the best with that. If you have any questions about quantum computers, feel free to reach out to us either via our social media channels or also to me personally. Thanks, guys, and have a great weekend.